So in this lecture 6, we are going to think about the electron conduction in solids. So basically how electrons can move around under the atmosphere of the positive lattice. Okay. So at first, let's think about the free electron approximation. And as you can see, in solids, there are many atoms, as I mentioned frequently. So this is a difference between the molecules and solids case. And if you have many solids, atoms, you have the high density of the ionic lattice, meaning that if electron is a negative charge, the nuclei has the positive charge. So electron is a kind of like moving around in the positive charge, positively charged lattice, and this lattice has a density about 10 to the 22nd per cubic centimeter. And in the solid case, these electrons are not only staying near only the single atom, but these electrons can move around for different atomic positions. However, in many theoretical studies and observations, actually this electron can move around freely. That's why it's called free electrons. So even if you assume the flat energy throughout the materials, that's a kind of good approximation for free electrons. So if you're interested in it, maybe you'd better deeply follow the solid physics textbook, what we are just going through. But as a possible approximation is a periodic boundary condition. This is the first approximation of the potential of the positive lattice. And in this case, the Schrödinger equation can be described like, so we are now thinking about K. So each K vector electron, X, Y, Z, we can describe just like R equal epsilon, maybe K with psi, K, X, Y, Z, right? This is the Schrödinger equation. And under the periodical boundary condition, we can assume that wave function also have some periodicity. So psi K R can be described as some constant times exponential I K R. And if you apply the boundary condition to this wave function, meaning that just this wave function is a periodical function, and by adding L, meaning the lattice interval. So every lattice interval, this psi K must be equal. And this one also given in the exercise, but you can easily obtain, you can easily estimate this one, right? So this second equation, and just you put the R psi R equal psi R plus L, and K is now limited and quantum limited to some depending on the quantum number. So in the K, in the one-dimensional case, by Lx over L, and Lx equal one, so some integer, and similarly, so L 2 pi, Ly, L 2 pi, Lz, right? So just you can simply the wave vector of electrons are somehow limited by the size of the L. So and then there's some quantum number of Lx, Ly, Ld. So that means, as you can see, that this is a wave vector space in K, and every 2 pi over L, you have one K value. So the first one is 2 pi over L times 1, and second one is 2 pi times over L times 2, and so on. So for one K state, K wave vector, you need 2 pi over L distances necessary for electrons. And then it can be easily extended into the three-dimensional space, meaning that a wave vector space of 2 pi over L cube is necessary for one K state, for three-dimensional state, right? So that means that and the epsilon K, as we've already obtained in a dispersion relation, so epsilon of K equal h bar squared and K squared over 2m, which is equal to 2m h bar squared. And for each K space, you need to have 2 pi over L cubed. So Ly squared L Z squared, squared. So you can write like the energy of the K wave vector K electrons have the energy like this. So it's quantized